Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed the basic definitions of differential equations and how it is just appearing in the natural system or like industrial applications or engineering problems. And we have discussed also some of these solution techniques for first order linear differential equations. And in this lecture, we will start about these continuous time models on population dynamics. Especially these population dynamics models that has developed based on these differential equations, and we will just construct some of this population model based on this ordinary differential equations first, then we will just go for higher order differential equations. So, first in this lecture we will just go for like growth of microorganisms and how this model is developed based on this differential equation, that we will just discuss. Then we will just go for dependency of rate of reproduction on time and resources, and in the third stage we will just test the steady states, how we can just find a like a feasible state or the critical points for the development of these population levels. Then if the population level is increasing, then there should be some resources, and how these resources are acting in the development of this population level or increase of this population level, that we will just discuss in the last phase of this lecture. So, one of the simplest model using differential equation is the growth of microorganisms. Since whenever we will just consider any change of a variable with respect to any other parameter, definitely this will just provide us a differential equation. Since this growth of microorganisms is nothing but the change of size of the population or the change of size of different cells with respect to time or with respect to resources or with respect to like different aspects of physical phenomenon, that can be constructed as in the form of differential equations. So, the growth of unicellular microorganisms like bacteria, unicellular especially, since they are like individually they can grown up or they can be break to form like new cells, and the changes occurring in their population can be studied by simple differential equation, since either it can be like divided into cells to growth the like level of population there. So, that is why we can just construct a model where each of these individual or uniformly it can be divided to get the new cells thereover, and we can just formulate this model using these differential equations. We have already studied the discrete model for the same, since there itself we have just written this model as in the form of Cn as alpha Cn minus 1, which is called your cell division model. And especially for the growth of this bacteria, so we have to consider like a droplet of bacterial suspension is put into a flask or a test tube having some nutrient medium. This means that we have to provide a like a compatible medium where this cell or this bacterial growth can be possible. So, then we can just formulate this model. So, the culture is also maintained at compatible conditions, since if favorable conditions will not be supplied there, then this growth cannot be possible also. So, many restrictions are there, but first we will just go for this development of the model where there is a uniform growth of this population level due to supportive or the compatible condition to growth process of this bacteria should be provided. So, that is why we have just considered here the culture is also maintained at compatible conditions to help bacteria to reproduce by cell division process. At each time or at each level, the cell will be divided to give new cells, that the cell level can be like growth or it can be increased. So, after suppose certain time we can just find that this cell division process already if it is started, then after certain time you will have like huge number of population levels for the cells. And for a particular time level, suppose t we are just considering here, k is the number of new cells formed by cell division process suppose. That is, we can just write rate of reproduction per unit time is defined as k here. Rate of reproduction means that with respect to time how this cell division is occurring and how this population growth rate it is just activated, that depends on this parameter k here. So, obviously, if we will just consider this change of population level with respect to time, that depends on k and the number of a population present at the beginning. Hence, the model for growth of microorganisms will be in the form of like change of population of n there, which depends on this rate of change of this population level into the total number of population. So, if you will just consider that suppose this reproduction rate is constant, that is k is constant here, then the solution of this above equation, especially we can just write as dn by n as k dt here, and then we can just write ln of n as kt plus c here, any arbitrary constant. So, this arbitrary constant we can just assume as suppose like n0 here, that is the total number of population present at the beginning. Then we can just write this one as n equals to, or we can just define this one as in the form of log of n0 suppose. So, then we can just write this one as log of n ln of n minus this we can just also write as ln of n0. So, ln of n0 which can be written as kt here, then this implies that we can just write as ln of n by n0 as kt here. So, n by n0 can be written as e to the power kt. So, n equals to n0 e to the power kt here. So, this is the final solution. If the initial level or at a zeroth level or t equals to 0, the total number of population size is n0 at that point. So, this equation is known as Malthus law or the Malthus law of population dynamics. So, if we will just recall this one in a discrete time, so obviously we can just write, since in that sense we are just writing that modulus Cn equals to alpha Cn minus 1, obviously we can just write this one as alpha to the power n C0 there, which is also increasing in a exponential order. If instead of like cell reproduction, if there is a decaying or like extincting at the rate of k suppose, this means that the population level will be declined there, then the equation will be referred as a decaying population level, and especially in that sense we can just consider that this k is negative there. So, that is why this direct population level we can just put it as minus kt there, then we will have like n by n0. So, this is e to the power minus kt, and final level we will have like n equals to n0 into e to the power minus kt, where n0 equals to n of 0, that is nothing but at t equals to 0 we will have this population level as n0. So, if you will just show this one in a graphical sense here, then we can just find that there is a growth decaying rate. So, this should just come in the form. So, there is a exponential growth of a rate, that is a n0 e to the power kt, and if there is a decaying of a growth rate, so that should be like this is the population decaying rate there, it is just approaching towards 0, and finally we can just find that there will be no survival of the population if we will just t tends to infinity in that range. And especially in a like physical sense this does not happen, since the resources or like many physical restrictions, it will just prohibit this growth of this population level. So, certainly we can just find that this population level will not increase in an infinite manner, or it cannot be decayed to 0, that population will vanish. So, that cannot be happen, especially in a like physical scenario. So, many restrictions it will be there, and we will just consider these restrictions afterward. And if we will just go for like if the population size is doubled at a level, then this is called your doubling time period, and how much time it is required if we want to calculate. So, doubling time t is defined as the rate at which the number of cells will get doubled as that of the initial population. Initial population means we can just consider our solution, that is in the form of n of t is written as n0 e to the power kt. So, if the population size will be doubled from the initial population size, since we are just considering at initially t equals to 0, n is considered as n0 there. So, for that if you will just consider like n equals to 2n0 at a level, then we can directly replace here n of t as 2n0. This is nothing but n0 e to the power kt, and finally we can just write n0 will cancel it out. So, e to the power kt equals to 2, and then kt equals to ln2, and t if we want to calculate, so it is ln2 by k there, which is the final solution here. Similarly, for decaying population level, so if we required like the population size, it will be like half of the initial population size, then this is especially called half life period, that the initial survival population should be halved there. So, it can be defined at the time at which the number of cells will get halved. This means that this n of t can be replaced as like n0 by 2 there, which can be written as n0 e to the power kt. So, if you will just cancel it out, then we can just find t as like ln2 by k here. Since if you will just see here, that is a half it is there, and this is a like minus kt, it should be present there. So, that is why we are just finding this ln2 by k there, if it is half. Now, think of the parameter k here. Since k is the rate at which like we have just defined here, k is nothing but the rate of reproduction per unit time. Sometimes it may be like decaying, sometimes it is just influencing the increment of the population level. So, that is why we can just think of this parameter k, how it is just depending or how it is just acting inside the population level for the increment and decrement of this population level. Should it be a function of time or something else? So, with respect to time, whether k will get changed or not, that we have to also consider. If k depends on time, suppose it is generally known as Gompertz law, and generally there is no exact information of time dependencies. That means the time dependence behavior of k, but practically we can analyze that k should have direct or indirect dependency on available resources. Since if the resources are self sufficient, then this population level will grows off, and if suppose there is a limitation in the resource level, then this population level after a certain time we can just find that these cells will be struggle for the food and they will just get decline. Let C represent the concentration of resources available, then for k equals to, suppose k is a function of C here, that is the resources available there. Then the Malthus model can be reframed as like, since k is a function of C here, or the concentration level or the food or the resources whatever it is available there, then this change of population level that depends directly on k of C there, and it can be multiplied or used by the total population size. Now, the question is how resource concentration is varying with time. So, maybe sometimes we can just find that whether C is getting changed or this resource level it will be get like less after like 5 days or 10 days or a certain period of time, we can just find that C has also got changed. So, whether it is a constant function or a varying one, that we have to determine. Experimentally it is tested that the rate of resource concentration should decrease as the rate of population increases. Definitely this population size, they will use these resources, hence the resource will get reduced there. So, that is we can just write C prime as minus alpha of n prime there. That is, change of this resource concentration will depend directly in a declined form with the change of this population size, where alpha is a constant describing consumption of food by each new bacteria. Hence, the mathematical model for growth of population with resource dependent reproduction rate will be like n dash t, we can just write direct model here, k of C into n of t, and this consumption of this concentration by this bacteria, which can be written as C dash t as minus alpha n dash t. If you will just consider a simple case where rate of reproduction per unit time k depends linearly on available concentration, since there is no other restriction, directly they are just eating the food and they are just getting grown up. That is k of C, we can just write k into C there, where k is like a constant there. So, the model we can just write it as n dash t which was earlier written as k of c into n of t. So, that is why we can just directly replace k of c as n of kc into n of t, and c dash t it is especially written as minus alpha into n dash t, and n dash t directly it can be replaced by this minus alpha k c n of t there. To convert this system of two differential equations into a single differential equation, since directly we can just find the solution from the second equation and we can just put in the first equation. And this simplified case, if you just integrate this equation here, that is c dash t as minus alpha n dash t here, directly we can integrate, then we can just find c of t minus alpha is a constant here. So, minus alpha n of t plus a proportionality constant c0 here, where c0 is the proportionality constant. And if you just substitute this expression in a c of t back in the first equation here, then we can just write this equation as n dash t, and finally k c n of t is there. So, k n of t it is present. So, c is just replaced by c0 minus alpha n of t. And if we will proceed further, then we can just find that the final solution of this equation is in the form of n of t equals to a n0 by n0 plus a minus n0 e to the power minus gamma t. So, last lecture also we have obtained this same equation, and the solution we have just get it over there in a differential equation form, where we have just done the separation of a variable, and we have just have done some manipulation to get the solution there, where we have assumed n0 as n of 0 here, that is the population size at t equals to 0, that is n0, and the constants like a is defined as in the form of c0 by alpha, and gamma it has been kept as kc0. If you will just follow the previous lecture, we have obtained the solution for this differential equation. So, that is why we need not have to do it again. If we want to go for the steady state or the critical points we want to find for this differential equation here, then the steady state is defined as a state where the rate of population growth is 0, especially if you will just put here dn by dt equals to 0, then we will have a steady state there. This means that we can find there is a change of population with respect to time, it is 0 there. Then we will have like a steady state. With respect to time, there is no variation we have to find. And if you will just consider this one, if we will just find like our equation 13.9 here, that is n dash t, it is just written, or n prime of t, it is equals to 0 here. So, then we can just find that k n of t either it is equals to 0 or c0 minus alpha n of t equals to 0. So, if k n of t equals to 0, this means that k is not equals to 0, since it is a proportionality constant. So, obviously we can just get n equals to 0 there, and for the other side if you will just say that we can just get as c0 minus alpha n of t, this equals to 0. Obviously n of t can be written as c0 by alpha there. So, this is the parameter we have just defined here. So, the steady state is achieved either when we can just consider n equals to 0, or we can just consider n equals to c0 by alpha as a there. So, if you will just go for like for a growth size is suppose small here, very small, suppose we can just consider, then the square and higher power terms can be neglected. And further if you will just follow like our population level here, that is defined as n prime of t here. So, which is written as like k n of t into c0 minus alpha n of t here. So, first term it will just give you like k n of t c0, and second term it will just give you like k alpha into n square t. Since n is very small here, then n square can be neglected. So, we will have this first term that is in the form of k n of t c0 here. So, that is why we have just written here n dash t is approximated as like k c0 n of t here. That is, it will have exponential growth instead of logistic growth rate. Directly if you just find the solution, it will just provide us an exponential solution there. That is n of t equals to some constant into e to the power like c0 Kc0 we can just get it over there. Kc0 into T we will just get. And now if you will just analyze this like population level at a critical point or like a steady state, if you will just try to find it out. So from the graphical sense, if you will just see here, for both high and small initial population, we are just finding that the population is approaching to a steady state, that is n equals to A here. And the steady state n equals to 0 is unstable, since we will start with certain population there, and we cannot find that this population level will be 0 and we can start the experiment, or we can just we can expect some like some population level if we do not have any initial population size. So that cannot be expected. So that is why we can just consider the steady state n equals to 0 is unstable, because we need certain population at the beginning to get the growth of this population size. So it is just if you will have certain population level, then we can just find that this population is approaching to A whenever this time proceeds at a critical stage. So if we just consider this growth of microorganisms, so we have analyzed the behavior of population growth for both high and small initial population, when population rate function has a linear variation with respect to available resources. This means that if you will just consider this behavior of population growth at a like high population size or like a small population size, so this population size variation, it is always showing a linear variation with respect to this available resources. Since whenever these resources are like limited, then either if the high population it is there, they can eat, and after certain time whatever these resources, it will be like feedback or like feeded there, or it can be available. So certain population will be died it out and it will just maintain a proper ratio there. And if it is a small population level, suddenly if they have a huge amount of foods, they can just grow it off, and after certain time they will struggle for the food and they will maintain a proper linear rate there. And this linear variation of resources implies that resources are unlimited, but practically we have limited resources. So resources either we can just provide or whatever it is available, so it is always limited. So that is why this population level always they will just try to maintain their balance for the growth or decaying process. Then if the limited resources is available, how our model will like treat there. So to model this kind of culture, we used to devise we use a device called chemostat, since that if a culture medium it is there, so we are just supplying some food, how this proper utilization of food is occurring inside the system and how the output is just coming, the total process it is called chemostat. So these things we will just discuss in the next lecture. And in the present lecture we have discussed like first the growth of microorganisms, that is we have just considered a simple differential equation, that is the population size it is just getting changed with respect to time, which is defined in the form of dn by dt, and which is directly proportional to the like rate of change of this population size and with respect to like the total population available at the beginning. And based on that we have just find some solutions. So that solution just reflects as like sometimes this population level is growing or like increasing in an exponential manner, and if it is decaying or if k is just taking a negative value there, then this decay rate it is just occurring in an exponential decayed manner. And if we want to calculate also the doubling time, this means that population size it will be doubled after certain time. So that time level we can calculate also, that we have computed in our calculation. And sometimes if the decaying is also occurring, then after like certain time steps we can just find this half of this population level, that time level we have just computed also. Then in the third phase we have discussed the variation of a rate of reproduction with respect to time and available resources. So C as a function of like k we have just considered, or k is a function of C, then C can be like dependent on this population size increment and decrement level that we have discussed. Then in the fourth stage we have just considered this linear variation, since the available resources they are limited, and based on that how this population level is increasing or decreasing, that we have tested. And in the last to second one we have just considered the stable and unstable steady states. So it is very important, since we have to consider like critical points to find this solution growth rate or like decaying rate, or how it is just approaching to a stable solution process. Since stable means like whatever this resources or like barriers we will just provide them, but after certain restrictions also they will just maintain the same level. So that is why it is very important to discuss the stability and the instability issues for this like growth of populations. So last is we have just discussed that how this population level will like varied with respect to the resources available. So if the resources are like limited, so even if this restriction it is there, but the population level it will just grow GT of there. And if the resources can be like plentifully available, sometimes we can just find that this population level will also maintain the same level when we will just go for like stability condition for the steady state. Thank you for listening this lecture.